sektörün değerli temsilcileri, TÜDOKSAT, Türkiye Döküm Sanayicileri Derneği, TÜDOKSAT'ın Sanal Eğitim Organizasyonu TÜDOKSAT Akademi'nin düzenlediği bir etkinliğe daha hoş geldiniz. Yine bir webinar. Seminerleri fırsat oldukça yer veriyoruz ancak webinarlarla devam etmek de hepimizin bir şekilde işine geliyor. Zaman yönetimi açısından seyahat zorunluluğu olmaması, bulunduğumuz mekandan katılabilme nedeniyle. Kısaca TÜDOKSAT Akademi'nin etkinliklerinden bahsetmek istiyorum. Bizim bu ay boyunca, Temmuz ayı boyunca 3 etkinliğimiz var. Bu ikinci etkinliğimiz. Konuyu biliyorsunuz. Ee, Demir dökümhanelerinde termal analiz yoluyla prosesin kontrolü. Bir konu, güzel bir konu, iddialı bir konu. Konuyu ancak iyi bilenlerle anlatılabilecek ve anlaşılabilecek bir konu. İlginizi çekeceğini bekliyoruz. Ee, Bundan sonraki bir önceki webinlerimiz farklı bir şeydi. Teknik olmayan bir konudandı. Finans konusunda yönetici adaylar için finans. Bundan sonraki konumuz gene finans ama arada teknik olan konulara daha fazla ağırlık verdiğimizi görerek teknik olmayan konulara da zaman zaman yer vermeye çalışıyoruz. Bu seminer, webinar döngüsü devam edecek. Ne zamana kadar? Kongremize kadar 19-21 Eylül tarihlerinde İstanbul'da düzenlenecek, Ankiros'la birlikte düzenlenecek Türk Cast fuarları sırasında 12. Uluslararası Döküm Kongremizde sektörümüzden gelen iyi uygulama örneklerini değişik uzman arkadaşlarımızdan dinleyeceğiz birlikte. Şu anda seminer teknik tebliğleri değerlendirme aşamasındayız. Aynı zamanda bir de çağrımız oldu. Ne için? Çevre ödülü için. Çevre ödülü için de ilgili kuruluşlar dosyalarını hazırlama aşamasındalar. Orada da Erdoğan'a çevre ödüllerini vereceğiz bu yıl gene. 2 yılda bir bunu mutlaka gerçekleştiriyoruz. Şimdi bugünkü konumuzu Foseco ile, onlar VESUVİUS diyorlar ama biz hala Foseco olarak biliyoruz. O ayrımı iyi bilenler kapsamın nereye kadar, VESUVİUS'un nereye kadar sorumlu olduğunu, Foseco'daki Türkiye'nin faaliyet alanlarını bilirler. Foseco'nun bu kez uzmanı Mr. Joao Portekiz'den geliyor. Portekiz'den paylaşacak. Ancak sunumunu İngilizce yapacak. Ekranda görüntüleri Türkçe olarak deneyeceğiz. Ekrandaki görüntülerin Türkçeleştirilmesinde de Foseco Türkiye'den Alper Seçkin arkadaşımız görev aldı. Kısaca kurallarımızdan bahsetmek istiyorum. Lütfen sorularınızı sohbet kutucuğuna yazın. Webinar sonunda onları kendi sunucu arkadaşımıza, uzman arkadaşımıza soracağız. Türkçe'de yazabilirsiniz, İngilizce'de yazabilirsiniz. Her iki dilde de soru yazmanız mümkün. 1 saatlik süremizde sunuş yapılacak. Devamında soru cevaplara geçeceğiz. Sunumun sonunda memnuniyet anketimiz var. Onu cevaplandırmayı unutmayın lütfen. Bu videonun kaydı tutulacak. TÜDOKSAT Akademi web sitesinde paylaşılacak. Ama sunumun kendisini elde etmek isteyen, yararlanmak isteyenler Foseco Türkiye'ye Alper Seçkin arkadaşımız aracılığıyla ulaşıp onlardan edebilirler. Onların paylaşmakta sakınca görmeyeceklerini düşünüyorum. Konu teorik, sıkıcı gelebilir ama gelmesin lütfen. Çok iyi hazırlanmış bir sunum. İçeriği çok zengin bir sunum. Soru sormaktan da mutlaka kaçınmayıp ilgiyle dikkatlerinizi vermenizi bekliyorum. Mr. Joe, could you welcome first?
Thank you. Thank you
Uh,
very much.
Thank you for your very hard work to present
Thank you.
your detailed topic with us. Uh, you have got 60 minutes presentation time, but don't be in a hurry. The topic is quite interesting and important for us.
Thank you.
Could you introduce yourself first and then start presentation? Thank you.
Of course. Of course. Thank you very much for the presentation and for having me. and the rest of Foseco team in this webinar. My name is Joao Teixeira. I'm Portuguese. I work at Foseco since December 2022 as an application engineer for Europe for FMT products. I started working in ferrous metal treatment since 2014, since I finished my my college degree. I worked mainly with cast irons, but I also have some experience with non-ferrous, with aluminium and brass alloys. But most of my work has been developed with cast irons, especially nodular cast irons. And I will start now the presentation. So what we'll discuss during this this 1 hour presentation is the importance of thermal analysis and process control for cast iron alloys, for production of cast iron alloys, what we can do, and how could we improve the overall quality with thermal analysis and quality control. So this is basically the main topics that we will address during this presentation. Just a quick overview regarding the solidification of cast iron alloys, just for us to remember some things that we learned in university, just some notions, some topics regarding solidification. The second main topic, ferrous metal treatment, magnesium treatment, inoculation treatment, the importance of each process, and what we could do to improve them, and what we could do to improve the overall quality of the cast iron in this with these steps. And the last topic, the third topic, thermal analysis and process control. So basically the use of thermal analysis to help achieve a high quality cast iron for production. So the first topic, solidification of cast iron alloys. We will start with the basics. Basically, all of the solidification happens in cast iron. First, we have liquid metal, and when we are removing heat from the liquid metal, so when we are solidifying, we have the formation of stable nuclei. This is the first step for solidification. And as time goes on and we lose temperature, we lose heat inside either the ladle or inside either the mold, these nuclei start to grow. They start to go against one another, and they start to solidify in what we call a cast iron part, the component that we are producing. So basically, the first step is the solidification of a stable nuclei, growth, and the formation of grain boundaries when all these grains starts to go against one another. This is a simple explanation of how cast iron alloys solidify. And we have two main types of solidification, of nucleation of stable nuclei. We can have a heterogeneous nucleation. This is what we are trying to achieve with the use of inoculants. So basically, we are giving the liquid metal the stable nuclei for the nucleation to start. So basically, what inoculation does to the liquid metal is adding points of solidification for the stable nuclei to start to grow. This way, it's less energy consuming, and we can achieve a solidification in less time than if we don't have any type of inoculation. Sorry. The other type of nucleation is what it is called homogeneous nucleation, and this one is achieved when we don't have any type of inoculation. So when you don't give anything for the stable nuclei to grow to the liquid metal, and we just give time for the solidification to happen, this type of nucleation takes a long time. Normally, we don't like this because, as mentioned, it takes longer time, and we have a lot of problems associated with this, especially with the presence of carbides. So again, it's a second part of the importance of inoculation. is to achieve a quicker solidification by adding stable nuclei for the nucleation to happen, and to allow time for the carbon to transform in graphite and not in carbides. So inoculation has these two different important aspects on it. And in this image, we can see the big difference between having an heterogeneous nucleation and homogeneous one. At the end of the heterogeneous nucleation, you can see that we have a lot more stable nuclei than comparing at the same time with the homogeneous one. So inoculation is a really, really important step in cast iron production, mainly for this, for the stable nuclei to be added to the liquid metal. And this is basically the scheme of how solidification happens in the liquid melt. If you don't give anything to the liquid metal, the solidification happens from where it is colder to where it is hotter. So when we pour the liquid metal to a sand mold, a green sand mold, for example, the solidification happens from the boundaries of the sand mold to the center. So it's one direction only. Only at the end, and you can see here in the image, only at the end, we have what it is called axial grain size, grain boundaries. So they are not one directional. They are nucleating randomly in the melt. The main objective with the inoculation step is to have this type of nucleation happen at random spots inside the mold and not have a one direction solidification of the cast. And this is basically what we have with heterogeneous nucleation. So we are adding an active element, barium, zirconium, aluminium, calcium, bismuth, lanthanum, wherever we are heading. There are some differences that we are going to discuss later on, but we are heading a substrate for the nucleation to happen. And it is basically what we have in this image. We have a substrate and the nucleation happens around the substrate. The graphite particle grow around the stable nuclei that we gave to the liquid metal. And nucleation happens after that. So we have random spots inside the liquid metal with stable nuclei. The stable nuclei start to grow, to get bigger as time goes on, as solidification happens. They start to grow, they start to get bigger, they start to go against one another. And at the end, we have what I showed in the first picture. We have grain boundaries and we have a lot of stable nuclei growth inside the liquid metal. What we have here is the scheme for all type of ferrous and non-ferrous solidification. So this type of solidification is the same, either we are dealing with cast iron, either we are dealing with aluminum alloys, either we are dealing with brass alloys. The basis of solidification is the same. Stable nuclei, growth, and grain boundaries at the end. And this solidification happens always the same. As you can see here, these are what we call dendrite branches. And these dendrite branches start to go against one another and they start to solidify together. And this type of solidification happens in all ferrous and non-ferrous materials. So it's the same. Either we are dealing with cast iron, with aluminum, with brass alloys. The bases are always the same. So just a quick summary of what we discussed until now before going to the next topic. So really important to control and really important to know during solidification. Chemical composition, because we are adding inoculant agents, we are adding magnesium agents, so we are adding a lot of different chemical compositions to the melt. So we need to have a correct understanding of what we are adding and the effects of what we are adding. Solidification happens always in the same manner. Formation of stable nuclei. This is helped with the inoculation process, the inoculation step, because we are adding active elements to help the formation of stable nuclei. Stable nuclei grow. They start to go against one another and to form crystals and to form the grain boundaries, grain structures that we see in the microscope when we polish a sample and we go to a microscope to have a metallurgical analysis. And basically, we have two types of solidification. Homogeneous solidification, where we don't do anything to the melt, so we don't help the melt with inoculation. So the solidification happens during time, it's less effective. And the heterogeneous nucleation, where we help the melt with the addition of inoculants. And this was just for us to remember some concepts and to align some concepts, general concepts of solidification. Again, this is really important. Most of the considerations that we are going to discuss here regarding solidification, they are the same for all types of materials. So the basis and how things work, they work the same. Either we are dealing with cast iron, with gray cast iron, with compact, with nodular. Either we are dealing with aluminium alloys and all the other types of alloys. And we are going to start with the study of the carbon-iron diagram, phase diagram. And we are going to start with the ferrous metal treatment part of the presentation. So pretty basically, we are going to discuss the magnesium treatment, the inoculation treatment, and the importance that both steps have in production. So basically, to start, all of us know the definition of a ferrous alloy, but we are going to start here in the with the basics. So basically, we are dealing with cast iron, and cast iron is a ferrous alloy. So most of the main component of a ferrous alloy is iron. However, we are dealing with cast irons, and cast iron is a really particular type of material, because even with iron being the main element present, we have a significant amount of carbon as well. So what we call cast iron is basically iron and carbon. An opposition of steel. Steel is mainly iron and with a low percentage of carbon. So if we are dealing with cast irons, we are always dealing with the relationship between iron and carbon. And one of the easiest ways for us to understand the relationship between iron and carbon is by studying the phase diagram. And the phase diagram is basically a graphical representation of the physical states or phases that change under temperature and under pressure and under chemical composition. So in here we have the most simple one that we have, the water phase diagram, and you can see all the different stages of the water, either gas, liquid, or solid, in the 2D phase diagram. And for carbon and iron, it is basically the same. We are having a representation of all the different stages depending on temperature, pressure, and chemical composition of cast iron. And we have a couple of important spots to know and to discuss. One of the main ones is the point where we differ between steel alloys and cast iron alloys. So as we discussed, steel is basically iron with a low percentage of carbon, and the separation is around 2% carbon. So everything lower than 2% carbon is considered steel, so it's not cast iron, and we are not going to discuss here. Everything to the right of the 2% carbon is considered a cast iron. So this is a really important point for us to distinguish between steel and carbon. And another important point is the eutectic point that we have with 4.3% carbon. This is the point of separation between the three different solidifications that we can have with cast iron. We can distinguish cast iron, and again, this is the same for graphite, for gray, compact, and modular. The concepts are the same. We can distinguish the solidification type based on the amount of carbon that we have. If we have 4.3%, we have the eutectic point. We call it a point, but in reality, it's more of a smaller area. It's not considered a point, but for easier explanation, we call that a point, around 4.3%. It's an eutectic solidification. It's a eutectic point of cast iron. If we have less than 4.3%, we have an hypoeutectic solidification. And we have more, and if we have more, we have a hypereutectic solidification. And we are going to see that this is really important for understanding the solidification and for understanding the different impacts that we have, especially in the gating system and in the mechanical properties of the cast. Before going to that, just an overview of some important points of the phase diagram. So everything over this line is liquid. So this is a liquidus curve. Everything over this line is considered liquid. In here, we have a semi-solid state. So we are losing temperature inside the ladle or inside the mold. We are losing temperature, and they are starting to have a mix of solid with liquidus. And in this part, the solidus part that we have is austenite. And on the other side, we have the same situation. We have a mix of liquidus and solidus, but the solidus phase that we have is not austenite, it's graphite. And we are going to see that this is really important for a lot of different reasons. And we have the eutectic level around 1151, 1152. This is the separation between the semi-solid state to the 100% solid state. So everything lower the eutectic point is solid. All the points on the left, they are for steel. They are not particularly important for us. And the other and the last one, so everything lower than the eutectic point is solid, and it's always a mix of austenite and graphite. The percentage of each, it depends on what type of solidification that we have. So it depends if we are having a hypoeutectic with more austenite being formed at early stages of solidification, or if we are having a hypereutectic solidification where more graphite was formed at early stages. And in here, you can see the different steps for the solidification of the different types of cast iron. So for hypoeutectic solidification, and this is, again, this is with carbon percentages lower than 4.3%. So we are on the left side of the eutectic point. And it doesn't matter if we are really far away from the eutectic point or really close to the eutectic point. The whole area is considered hypoeutectic solidification with different impacts in mechanical properties and solidification, but it's all considered eutectic solidification. And we can see that we are going to lose temperature. We have a point here. It doesn't matter the percentage that we are going to have for carbon, and they are losing temperature. And when we reach the liquidus temperature, so when we reach the point where we have a mix of liquidus and semi-solid state, the first semi-solid state phase to solidify is austenite. So we have liquid metal and we have austenite being formed. And we are continuing to lose temperature. And when we reach the eutectic point, the eutectic levels, sorry, at 1151, 1152, around these temperatures, we have the start of the graphite phase. So after this point, we have a mix of austenite and graphite being formed. And this is what happens until we have the cast part solidified. So after this point, it's a mix of graphite and austenite. And the same thing, the same principle is used for hypereutectic solidification. So we have a point, we are on the right side of the eutectic point, so we have more than 4.3% carbon. And when we reach the liquidus curve, the first phase to transform is graphite, not austenite. And this is really important for a lot of different reasons. The main one is for the gating system, for the design of the gating system. When you have a lot of graphite being formed really early during solidification, we have what we see here in this small picture. We have big nodules and we have small nodules. So we have a really quick expansion of the graphite. This is important for some applications where we need this quick expansion of graphite. But at the same point, we have a lot of problems with this. The main one is that the graphite being less dense than the liquid metal, the graphite nodules or the graphite, I said nodules because I'm thinking about nodular cast iron, but the graphite being less dense starts to go to the surface and it can block the gating system. So we always have to be we have to pay a lot of attention to the type of solidification that we have. And this is one of the main reasons. So we have a lot of graphite being formed at early stages, really big one, really big nodules if you are talking about nodular cast iron. So we have a really quick expansion. And when we reach the eutectic level, we still have some carbon in the melt. We still have some nodules that are going to form, but they are smaller. So we have less expansion. So if we need, for some reason, to use the expansion of graphite at this stage, we don't have a lot of carbon in the melt for that to happen. So we have problems like shrinkage and micro shrinkage because we use the type of solidification that was not adept of the gating system or the type of cast that we are going to produce. And after the eutectic level, we have exactly the same for hypoeutectic. We have a mix of austenite and graphite being formed and growing until we have the cast completely solidified. And the last stage, that is a mix of hypo and hypereutectic. It's when we have what it is called eutectic solidification. So when we are really close to the eutectic point, and again, we call it the eutectic point, but it's an area, a small area around the eutectic point, around 4.3%, and austenite and graphite grow almost at the same rate. Most of the applications tend to look at this type of solidification because we have the best of both worlds. We have the expansion of graphite and the solidification of austenite happening at the same time. So to counteract some problems like shrinkage and porosity, normally this is the type of solidification that companies try to achieve. It is not easy because it's a smaller area to control. So the chemical composition needs to be really, really controlled. But normally it's what the companies try to achieve in most of the casts. So this is the different types of solidification that we have with cast iron. And as already discussed, this is not the only thing that we need to understand during solidification, because we are going to add a lot of different chemical agents, chemical alloys to the melt during solidification. If we are dealing with compact and nodular, we are going to add magnesium to change the shape of the graphite. But either we are dealing with gray, compact, or nodular, we are going to add inoculants to try to promote the transformation of carbon in graphite. So we have both treatments happening. Ferrosilicon magnesium to modify the structure of the graphite particles, to go from gray to compact to nodular based on the amount of magnesium that they are going to add, and inoculant with active elements to promote a stable solidification of carbon. And the stable solidification of carbon is basically allowing carbon to transform in graphite and not to transform in carbides. Most of the cases where we found carbides in the cast, they are because the inoculation process failed at some point. Either it was not enough to allow the transformation of carbon in graphite, or it wasn't strong enough, so we need a stronger active element like lanthanum or bismuth, or we have problems with the gating system, with the design of the gating system, and they are having some areas of the cast that are isolated and they don't receive enough liquid metal to transform the carbon in graphite. In here we have a lot of text, but this is basically the description of what we are discussing so far. So with inoculants, with the nucleation and growth of graphite, and the use of inoculants to promote heterogeneous solidification, what we are giving is time for the carbon to transform in graphite. So we are increasing the window of time for the carbon to transform. And when this happens between the stable temperature and the metastable temperature, so when this happens between 1151, 52 degrees and 1125 degrees, when the inoculation happens between these temperatures, normally we don't have problems with carbides. Everything that you see here in this graphic is where the inoculation is going to affect. So if we are between these temperatures, normally you don't have any problems. And an easy way to find if we are between these temperatures is with thermal analysis that we are going to discuss further. Normally, when you have problems with carbides, it is because the inoculation step was not enough, and we still have a lot of carbon free in the melt at lower temperatures. So if we are lower than the metastable temperature, again around 1125, 1120, if we still have a lot of free carbon in the melt, the carbon will start to grab all the elements that are in the melt. So chromium, boron, molybdenum, all the elements that carbon has a lot of affinity with, carbon will grab all those elements in the melt and it will form carbides. So with this, we can understand that we need to play with two different things for us to have a good inoculation step. We need to have inoculants, ferrosilicon with some active element to promote the formation of stable solidification of graphite. And we need to also be careful with the carbide promoters that we have in the base metal. The chromiums, the boron, vanadium, titanium, elements that we normally receive from the steel scrap or from ingot or from pig iron, we need to have a lot of, we need to have we really need to be careful with the amounts, with the trace amounts of these elements to have a good inoculation step. Because even if the inoculation step is really, really good, if you really have a good inoculant agent, but we have a high amount of these elements, we'll probably have a lot of carbides, because the affinity of carbon is really high with this type of elements. So it's easy for carbon to go and grab these elements that are free in the melt. So we need to play with both areas, with a really good base metal, with a low amount of these trace elements, and choose the correct inoculant for the process that we are going to have. And this is basically what inoculant is. It is a ferrosilicon alloy with some active element, with some barium, aluminium, calcium, manganese, zirconium, some, as everything in life and everything in cast iron production, some elements have good effects. After some time, they lose the effects. They have a quick fading time, like bismuth and lanthanum. They are really good for late stage inoculation, but they are not so good for early stages, for ladle inoculation. We have the universal inoculant with barium, with zirconium. So there are dozens of different inoculant agents in the market, and all of them have some positives and some negatives, even if it is the price, improvement of mechanical properties. Some inoculants are more specific for gray iron, for example, with the strontium ones. Lanthanum is really good, but as mentioned, the fading resistance is lower. Cerium is really good, but in some particular cases, it could be harmful to the production of nodular cast iron. So we really need to play with all the different types of inoculants that we have, and we need to be careful with the ones that we choose, because there are dozens in the market, and most of them, they have different applications for production. And in here is just for us to quickly see the effect of inoculation. In this picture, we can see the nodule count related to the section thickness, and you can see that we have two different types of inoculation. We have metal streams, so late stream inoculation, and we have ladle inoculation, so early stage. And you can see that the nodule count is decreasing with the section thickness. So section thickness being increased means that the solidification time is also increasing. And for these particular cases, we have to be really careful with inoculation, because we need to give a lot of stable nuclei to the melt to start solidify, because the solidification takes so long that after some time, some of the inoculants that you are going to add could disappear, and we don't have the effects of them in the melt. So we need to be really careful with them. And you can see that there is an effect of the type of inoculation that we have with the nodule count that we get in the cast. And the same principle is used for the right picture. We can see that increasing the silicon content, we increase the nodule count. Silicon is really important as an element heading to the inoculation, because it's the element that increases the window between the stable and the metastable temperature. So we can see that even by adding a simple silicon alloy to the melt, we increase the nodule count in three different sections of the cast. And in here, it's just for us to see the different types of inoculation that we have. We can have a preconditioning. Preconditioning could be done in the melting furnace or the ladle treatment before any type of treatment. We have ladle inoculation. Normally, it is done before magnesium treatment, for example, when we do the tapping between melting furnace to treatment ladle. We can do wire inoculation. It's a type of ladle inoculation. The only difference is that the inoculant is wrapped in a thin steel, and we have late inoculation. Could be metal stream inoculation with MSI that we are going to see further on, or in mold inoculation. And we can see the different elements that we are going to have in the different stages of inoculation. Again, ladle, in-stream, or core wire. And for example, for in-stream, we have the MSI unit. Normally, in-stream is really popular, especially for the automotive industry, for the production of smaller casts, where we really need a lot of speed and a lot of production capacity. And it is an easy system for us to have a high replicability of the process. So we are always having the same amount of inoculant. So we can compare one cast with another on the basis of the inoculation, because we are always having the same amount based on the amount of metal that we are pouring to the mold. This is an example of the MSI unit that Foseco commercialized, and it's really popular, especially for the automotive industry. And in here is just for us to discuss a little bit the differences when we are dealing with gray and with nodular. The principle is the same, solidification inoculation process. The principle is exactly the same, but the end game is a little bit different. So for gray production, we are not going to add any magnesium to the melt. So there is no change in the type of graphite that we have at the beginning and at the end. And the main objective of inoculation for gray cast iron is to promote the solidification of type A graphite. Is the best one to improve the mechanical properties. So inoculation is there to promote that type of graphite. And normally for gray cast iron, inoculation favors a pearlitic structure. So it favors a pearlitic matrix. And this is not the case for nodular. To have a pearlitic matrix with nodular cast iron, normally we need to add either copper or tin to the melt. And the objective is to have a lot of different spots for the germination of the graphite nodule. We are going to also add magnesium to promote the transformation from gray to nodular. And inoculation is there to give a lot of solidification points for the nodules to grow. And in here, we have the main active elements for inoculants. There are some other elements that are not present here, and there could be a lot of playing between one and the other, but basically it's barium, zirconium, they are the universal ones, aluminium. It's also used in 99% of the inoculants. Aluminium is really important because the crystal phase of aluminium is the same phase as for graphite, so it's easy for graphite to grow on top of aluminium crystal phase. Bismuth, rare earth, strontium ones that are really used for gray, cerium, lanthanum, and then a combination of different active elements. Bismuth, lanthanum, bismuth, rare earth. We can play a lot with this, and again, we have dozens and dozens of different inoculants in the market. And in this picture, it's just to illustrate, because since we are adding a lot of different elements to the melt, these different elements are going to have some role at the end. And it is really important to understand what the different elements are going to, how the different elements are going to impact the solidification and the overall quality of the cast. And you can see here, these dot lines are the stable and the metastable temperatures. So there are the temperatures where the transformation of carbon happens, the transformation of carbon in graphite. And you can see, for example, that silicon improves this window of transformation. But for example, chromium, vanadium, titanium, so elements that have a lot of affinity with carbon, they close this window. So if you have a base metal with a lot of chromium, titanium, we have less time for the carbon to transform in graphite, and it could have a lot of carbides. This is just for us to understand that everything that we have in the base metal and everything that we had during production will have some effect during solidification. And the other treatment that we normally use for cast iron, in this case only for compact and for nodular, is the magnesium treatment. And the main ones are the sandwich treatment, sandwich treatment, simply pour on top, core wire that is really popular at the moment, and in mold nodularization. And the main goal of this step is to change the structure of the graphite. So we start with the gray structure, with the fine lines, worm-like structure of graphite. And each time we had a small amount of magnesium, we change the structure of the graphite. And we go from a worm-like structure to a nodule structure. And we can see here that this is done by adding magnesium. So if you have a low percentage of magnesium, you have the gray cast iron that we know. And when we are going to increase the magnesium rate, we are going to change the structure of the graphite. Another element that is really important when we are dealing with different types of cast iron is sulfur. The sulfur for the base metal is really important because normally it could be higher when we are producing gray cast iron because sulfur does not impact a lot the shape of the graphite because sulfur basically is blocking the growth of the graphite. But when we are dealing with nodular, normally we want less amount of sulfur. So we need to be extra careful with the amount of sulfur. Again, because sulfur is blocking the growth of the graphite nodule. And the magnesium amount that we had during treatment is basically to catch the sulfur that is in the melt. So if you have a lot of sulfur, we need to increase the magnesium treatment. So we need to waste more magnesium during treatment. This is just an example, the change between the different types of gray iron that we can have, and you can see that on the right side we have more graphite type A, so we have probably better mechanical properties and overall quality of the cast. In here, it's just for us to see the tensile strength, the difference in tensile strength between gray, compact, and nodular. So we have higher tensile strength with nodular. It's more difficult to produce, but we have more mechanical resistance in this type of iron. And when we are dealing with nodular, we have a parameter that is called nodularity. So it's the roundness of the nodule that we have. And the increase in nodularity also improves the mechanical properties. So we can play again a little bit with the alloying elements that we had to try to improve the nodularity. And there is a significant difference in some values of nodularity. So if you really need a high level of mechanical properties, especially for safety components, for calipers, for the automotive industry, for brake systems, for most of the critical safety components that we produce with nodular, we really need to achieve a high level of nodularity. And some things that we do during process can drop the nodularity, like the magnesium percentage that is in the melt. Normally we need to be extra careful with the amount of magnesium that we are going to add, because after some point we are going to lose properties, mechanical properties in the melt. Again, the percentage of sulfur, because if we have more sulfur, we are going to need more magnesium, so we are going to decrease the nodularity. And some inoculants can also improve the nodularity in the graphite, and the nodule count, like lanthanum, for example, is one that is used a lot to increase the nodule count and nodularity of cast iron. And in here we can see just some microstructures of nodular cast iron, and you can see, for example, some problems that we already discussed. In these areas, we have a lot of nodules grouped together, so probably we have a really high hyperothetic solidification. So we have a lot of big nodules that grow together, and this could be detrimental for the mechanical properties. And if you look closer, we also can see that we have some problems with the nodules. They are not completely exploded, but we had some elements that were probably being harmful to the growth of the graphite nodule. So again, we need to be extra careful with everything that we had to the liquid metal, because it can affect a lot the mechanical properties of the cast. And this is really a quick example of the matrices that we can have with cast iron. We go from ferritic to pearlitic, and the tensile strength increases, but also the number of carbides increase. And we need to be careful, especially if the cast is going to be machined. We have to be extra careful with this. And the main difference between pearlite and pure carbides, pearlite, it's a carbide. It's iron and carbon carbide. But the difference is that we know the orientation, so it's always in the same orientation, and we artificially promote the appearance of pearlitic structure. When we have pure carbides, so chromium carbides or titanium carbides, they are random in the cast, and the orientation is not known, so we can have a lot of problems, especially during machining with this. And you can see here that they are oriented, all the pearlitic structure that we have, normally with the addition of copper and tin in nodular. They are oriented, and we know this orientation, and we know that if we had a specific amount of copper and a specific amount of tin, we are going to have a specific amount of pearlite. So we can play with these windows to improve the mechanical properties without decreasing a lot the machinability of the cast. And again, this is a sample analysis with pearlite. Normally we need to etch it with 2% metal to have this appearance, but you can see that we have the graphic nodules, we have the austenite around the graphic nodules, so we had a really close euthetic solidification. Both austenite and graphite grow at the same time, so we have a capsule of austenite around the graphic nodule, and you have the pearlitic structure around. And this is just to illustrate the differences in mechanical properties with the different types of matrix that we can achieve. And a small resume. So the phase diagram is important for us to understand the complex solidification process of cast iron and to identify the type of solidification that we are going to have: euthetic, hypoeuthetic, or hyperothetic. The main goal of the inoculation step is to promote the stable solidification of carbon and to limit the amount of carbides that we are going to have in the cast, sorry. And the main role of the magnesium treatment is to change the shape of graphite from gray to compact to nodular based on the amount of magnesium that they are going to have. And the last part, we are going to discuss a little bit thermal analysis. So we saw the phase diagram, and now we are going to see how we can use the phase diagram with the thermal analysis to determine a lot of different important topics during production. So thermal analysis, and again, this can be used for all type of production, in aluminium, copper, ferrous, non-ferrous. Thermal analysis is used in a wide range of alloy production, and it's basically the analysis of the changing properties of a sample, of a small sample, which is always related to temperature and time. So all the thermal analysis curve are always function of temperature and time. We have temperature and time, and we have the curve that is always based on these changes. For the particular case of Foseco, we use a Ferrolab 5, and it's a system that you see here. And the Ferrolab 5 is consisting of a cup and stand. The cup is where we pour the metal sample for the analysis. The ferro box, where we do the conversion of the thermic signal with the thermocouple type K to an electric signal for us to have a curve. And the workstation, where we can see the curve. And the stand is basically a place where we put the thermal analysis cup that connects the thermocouple to the whole system to convert the temperature in an electrical system. And thermal analysis can be used in different stages of production. It can be used in the base metal for us to know the liquidus temperature, the carbon content, the silicon content. Especially the carbon content is really important with thermal analysis, because carbon content is difficult to have with spectrometer, because being a metallic element, normally a system like LECO should be used to have a really, really high degree of correctness, sorry for the term, of the carbon content. It's really hard for the spectrometer to give this value correctly, and thermal analysis can do it really, really easy and replicability in time. And for this type of analysis in the base metal, we use cups with tellurium. And the tellurium is there to consume all the carbon and to transform the carbon in carbides, so to speed up the solidification process. So we don't have anything happening in the eutectic, so we have a straight line, and it's easy for the system to identify all the different spots that they need to identify. During production, after magnesium treatment, after inoculation, we want to see the changes in the melt with these production steps. So we use cups without anything. This is just to illustrate the differences between the correct filling and insufficient filling. Being a small sample, it is really important to always have the same amount of liquid metal in the cup, because the readings can differ if different amounts are present in the cup. It is based on the position of the thermocouple, and it is based on the total volume of liquid metal that is solidifying in the cup. So it's always important for us to have a correct filling every single time. And again, we have the phase diagram, and I just want to point it out that we are always talking about carbon content, but in reality, and as we already discussed and you are all aware, we have a lot of other elements that are present in the melt, especially silicon. After carbon and after iron is the element that we have in higher amount in the melt. So for the study of the phase diagram and thermal analysis, we change the carbon content for what it is called the carbon equivalent. That is a mix of carbon plus 1/3 of the silicon content. and we use this value to determine the point in the phasor diagram that we are the correct at a given time, either at production or in the base metal. And we can see here that the thermal analysis is basically mimicking the phase diagram. So every time we cross a phase in the phase diagram, we have a correspondence in the thermal analysis. So we change from liquidus to semi-solid state, we have an inflection. We reach the dielectric line, we have an inflection. So every time we have a phase transformation in the phase diagram, we have the equivalent in the thermal analysis. So we can always know where we are at a given point. And the curve is basically this. We have the main curve, temperature and time. The blue one is the first derivative. The first derivative is every time we have an inflection in the main curve, we have a zero, so we have a change of direction in the first derivative. It's just for us to have higher control of the points where some changes happened. For example, here we reach liquidus temperature and we have a change in direction. We achieved the minimum temperature. We have another change in direction. And you can see all the different parameters that we can control with thermal analysis. In this case, because we have a theoretical minimum and maximum, this curve was taken after production, so with the cup without tellurium. And we have values for the magnesium treatment, if we are dealing with, or the inoculation treatment if it was done. Another example of another curve is this one, and this is easier for us to see what I was talking about. We can see the undercooling, and undercooling is the difference between a theoretical minimum and the reference point. So the reference point is, as I mentioned, the stable temperature, close to 1151, 1152. And if you remember, we discussed that the inoculation step should always occur between the stable and the metastable. So between 1151, 52, and 1120, 25. So the minimum point during eutectic is the theoretical minimum. So if this point is above the metastable temperature, it indicates that we have a high percentage of success during the inoculation step. And it is what's happening here. We have 1136.5 degrees. So we are above the metastable temperature. So we have a 16 degrees undercooling. It's a difference between a theoretical minimum and the reference point. If the undercooling is smaller, it means that the inoculation step was more powerful. So we have a better inoculation step. The recalcitrance is the other value that we can study after magnesium treatment, and it is an important value based on the latent heat that is released during the nodularization of the cast. So it is basically what's happening between the theoretical minimum and the theoretical maximum. The temperature increases a little bit, and it increases because we have a phase being formed during that time, and the phase is graphite. So normally, if you have between 2 and 5 degrees recalcitrance for nodular cast iron, it's a good indication that the nodularization process was okay, and we don't have any problem. For gray, for example, the window is between 3-4 degrees and 7 degrees. It is a little bit higher because for nodular cast iron, we are forming a perfect round nodule. So the amount of latent heat released is lower than gray cast iron or compact cast iron. VPS, it's also an important value for us to study in the thermal analysis. It's it's an indication of the end solidification step. So it's this angle that we see here that is related to the end of solidification. Normally, if the VPS is lower, it means that most of the graphite was formed at the eutectic point, which is good for the soundness of the cast. So we don't have a lot of problems with shrinkage, micro shrinkage, and porosity. If the VPS angle is really high, and this is an example, it means that a lot of the graphite was still formed at later stages of solidification. So we can have a deficit of graphite being formed at the eutectic, and we could have some problems in the cast. And this is just a resume of what we discussed, that we use in the melting furnace the thermal analysis to control the carbon equivalent, carbon and silicon, liquidus temperature to know which point of the phase diagram we are and what type of solidification we have. And after treatment, you use thermal analysis to know the inoculation effect and nodularization effect of the process. So we already discussed this, but in this part we have the graphics. But for metastable, so with the cups with tellurium, the main objective is to only know the carbon content and the silicon content. So we consume all the carbon in the sample. We don't allow the carbon to transform in graphite. So we have a straight line at the eutectic point, as you can see here. So we don't have any type of transformation affecting the readings of the system. And this is just an example for us to understand that different values of carbon indicates different types of curves. We are at the hypoeutectic part, so we are on the left side of the eutectic point, but we have different amounts of carbon, and by having different amounts of carbon, we have different values for the liquidus temperature. So in the case of the blue point, we have a lower amount of carbon, so the solidification is happening really early on. So we are going to have some problems later on because we don't have enough carbon at later stages. So when we are below the eutectic point, you can have some problems with carbon. This is just for us to understand that we can determine the differences in carbon content with thermal analysis when we are dealing with the metastable solidification. And this is just a formula for silicon. It is dependent on the metastable solidification. The formula for carbon equivalent that we already discussed, and the formula for carbon that is dependent on the liquidus temperature, as we discussed 2 slides before. And in here, it's just for us to see that the different points in the thermal analysis represent different points in the phase diagram, like we discussed already. When we are dealing with the stable solidification, we have the 3 types of solidification that we already discussed: hypoeutectic, eutectic, and hypereutectic, and each one with the differences between the phases being formed first. Hypoeutectic with austenite being formed first, and the graphite being formed at the eutectic. The eutectic point, where the graphite and austenite form at the same time, so the inflection that we have at the eutectic is bigger because we have both phases being formed at the same time. And the hypereutectic solidification, where the first step being formed is graphite and later on austenite. And you can see that the curves are slightly different, especially the hypereutectic, because we have normally 2 inflections, big ones. The first big one with the graphite being formed at early stages, and a second smaller one with some graphite still being formed and austenite at the eutectic level. And this is a more detailed explanation of what we discussed: the hypothetic solidification, hyperothetic, and eutectic solidification. And in here with examples with microstructure, and we can see clearly that there are some big differences in the microstructure. We are dealing with exactly the same type of cast iron in this example, nodular, but slightly different values of carbon silicum, so slightly different values of carbon equivalent, means that we have a completely different structure in the cast. So we have different mechanical properties, we have different types of solidification that are going to affect the type, for example, of gating system that we are going to use, sleeves, etc. And you can see really clearly that for hyperothetic type, we have bigger nodules and smaller nodules. So we have the first phase of graphite being formed really early on, the big ones, and the second phase at eutectic, the smaller ones. For the eutectic, we have a more uniformed distribution of the sizes of the graphite nodules, and the same thing for hypoeutectic. The main difference between hypo and eutectic is, in this case, the nodule density. We have more nodule density at the eutectic phase because it happens in a single area, and it's not a mix of different points where the solidification of graphite happens. So we have a higher amount of nodules being formed in a single phase. And again, this is just for us to have an idea that different elements promote different types of solidification and affect differently the metal that we have. We have strong graphite promoters, so elements that are good for the transformation of graphite, silicon, as already mentioned, aluminium, as already mentioned again. We have elements that are not good for the formation of graphite, like phosphorus and arsenic. So we need to manage and we need to control these elements really carefully in the base metal. We have the carbide promoters, chromium, vanadium, that have a high affinity with carbon and can steal the carbon and transform carbon in carbides. And we have weak carbide promoters like tungsten and other elements that carbon does not have a high affinity with, so they don't affect the ability of the carbon to transform in graphite. And in this, it's just for us to see in more detail that the difference between the stable and the metastable temperature, so the stable and the metastable, it's between these temperatures that the inoculation step happens and the nodulization step happens. So it's really important for us to control how we achieve both these temperatures in production, and to understand that most of the treatments that we do should happen between these two temperatures. So we need to monitor them, and thermal analysis is really good for this. And we need to control the elements that we are going to add to the melt. And this is just to show that this is really important, especially for production, when you are moving a ladle from one side to the other to pour it to the sand molds. Each degree that we lose in temperature, it's 0.01% carbon equivalent. So we are losing carbon each time the temperature drops. So we need to also control really, really carefully the temperature when we are producing. This is, again, just for us to know the different elements and the effect that they have. This is just related to the importance of the eutectical minimum and eutectical maximum. The inoculation step happens between these two temperatures. And we can see here, this is a good example for us to discuss this. In the red picture, in the red curve, we don't have any type of inoculation. And in the green curve, we have a small amount of inoculation. And we can see that even a small amount of inoculation is enough to transform a lot of carbides in a lot less carbides. So we push the eutectical minimum from 1125 to 1139, and we improve the inoculation step and the ability of carbon to transform either in graphite or carbides. We improve this with a small amount of inoculation. This is just the importance of the eutectical minimum that we are discussing so far. And with the thermal analysis, we can also discuss the nodule density as well, because we have control of the magnesium treatment that we are going to do. And we can see here that with a small amount of inoculant, we can also improve significantly the amount of graphite nodules, because we are going to have more points for the graphite nodules to germinate. So we are improving the nodule density. And in this particular point, lanthanum, cerium, for example, bismuth, they are really important because they are really, really strong nodule density promoters. And normally when you need to increase the nodule density, and by increasing nodule density, normally you increase mechanical properties. These are good examples of inoculants that we should use. And another important aspect of nodular production is the nodularity and the control of the recalescence, the difference between the eutectical minimum and maximum. And you can see that when this recalescence is lower, we have a high nodularity, 80%, around 80%. And when it's higher, we have a lower nodularity, around 65%. So recalescence is also an important parameter to control in thermal analysis during nodular cast iron production. And this is just to illustrate normally the big problems that we have during cast iron production, the shrinkage problems. And shrinkage is basically a small area of the cast part that we are producing that at some point during solidification was isolated during solidification. And it was isolated because of dendritic growth, and we saw that everything, every alloy grows as a dendritic structure. The branches close early on during solidification, and they isolate a small area of the cast. And we have shrinkage problem later on because we don't have any liquid metal to expand and to counteract the contraction of the liquid metal. And one way that we can control this is with thermal analysis as well. It's a good indication, and it's a good tool to study the dendritic growth and and the expansion of graphite, and of course the careful use of feeders in the casts, especially the big casts. We need to be extra careful with the position of the feeders in production. For example, they always should have, when you cut them, they always should have a shrinkage inside. If they don't have a shrinkage inside, it means that the shrinkage is most likely inside the cast, or the position of the feeder is not correct, and we should move it. And for this, the easiest way is to use solidification modules and programs like Magma to understand where are the critical points of the solidification for us to counteract with the correct position of sleeves. And so the thermal analysis is important to control this dendritic growth, because most of the dendritic growth happens between the liquidus temperature and the eutectic low. temperature. So this is another thing that we can take from thermal analysis when we are going to study thermal analysis, and when they are going to compare a lot of different production data with thermal analysis. And this is just an example of some dendritic structures that you can find on some microstructure analysis. And this is just an illustration example of what is called dendritic coherence. It's the point where the dendritic branches close and isolate a section of the cast, and we have a shrinkage or a micro shrinkage because of this. Of course, we can counteract this problem in the particular case of cast iron because we have graphite, and graphite is the only element that expands during solidification, and we can use that expansion to counteract the problems of shrinkage and micro shrinkage. If we are dealing with steel, for example, or with aluminum or copper alloys, we don't have anything that is expanding during solidification. Everything is contracting. So we need to be even more careful when we are going to design gating system and all the systems to feed the die. And in here is just to illustrate at what points in the thermal analysis we have micro shrinkage and micro shrinkage. So all the micro shrinkage happens early on during solidification, and normally this has nothing to do with the metallurgic status of the bath. It's normally only because of incorrect position of sleeves, of feeders, or not enough feeders. So it's not a metallurgic problem, it's a design problem of the gating system and the feeder position. When we have micro shrinkage, so shrinkage that is really small, and sometimes it's not easy to identify micro shrinkage versus porosity. An easy way to identify is normally porosity is really perfect. The porosity defects, the holes are nearly perfect because it was gas that was trapped inside the melt, and the gas exploded at some point, but it's easy for a gas to stay as a perfect round than to stay in a different position. It's less energy for that state. So when the gas bubble explodes, that part was not filled with metal. So it stays a perfect round or almost perfect round shape. And micro shrinkage is it's everything but perfect. So one of the easiest ways to identify is the shape of the defect. And micro shrinkage, normally we can counteract it with better metallurgic control, with better carbon equivalent, better carbon silicon relationship, more control with the alloying elements that we are going to add to the melt. So there is a significant difference between macro and micro shrinkage, and when both of them happen during solidification. And just to finish, this is the Ferrolab 5, the system, the Ferro box and the workstation, and the cups that we are using at the moment to have the samples, tellurium and without tellurium. And this is a small resume of everything that we discussed. So the importance of thermal analysis to understand the physical transformations that happened during solidification using only a small sample. And it is important for quality control because we can use it in the melting ladle for control of the silicon, carbon, liquidus temperature with the cups with tellurium. And we can use it in production after treatment, after magnesium or inoculation treatment using the cups without tellurium. And we can check different parameters to check if the inoculation process or the non-inoculation process was okay, and if you have a good melt to produce and to have sound casts. And this is it. I'm sorry for the time. I tried to speed up a little bit, but I hope that everyone enjoyed, and please, if there is any questions or anything that you want to discuss, let me know. Thank you very much.
Thank you, Joe. That was really quite important topic. with too many aspects, so you
Yes.
cannot miss any of the topics. That's
Yes.
quite understandable.
Thank you.
That is quite understandable. Yeah, we are expecting some questions from the audience, and only a short message came from Alper saying that he has written his email address so that he will be ready to answer the questions which may arise after this presentation. TİDOKSAT'taki arkadaşlar memnuniyet anket sorularını yükleyebilirler şimdi biz sohbet ederken. Now, Joe.
Yep.
That's a topic. That's a hard topic actually to cover everything in a short seminar, so webinar.
Yes, it's true.
It is, yeah. It should be perfect if it becomes a seminar. Let me say half a day seminar.
Mm-hmm.
Oh, maybe we can organize together with Foseco Turkey a seminar, maybe next year, with a 3 to 4 hours time frame, and with the samples, with the sample cups, with the thermal analysis equipment, and so on. We may cover topics again once more, not only the theoretical topics but application examples.
Okay.
For example, you have mentioned from two type of cups, thermal equipment, thermal properties measurement cups, one with tellurium, the other one without tellurium. But we know that there is another cup which is ready to use nodularity of the samples.
With the sulfur.
Yeah, with sulfur.
Yes.
That's true. You did not mention from this one.
No, I did not mention because normally in everyday production, we can receive almost everything that we need with only these types of cups. You mentioned correctly the cup with sulfur is important, especially if we want to improve the magnesium treatment and if you want to understand the correct point of a magnesium addition that we want to add during treatment. But normally during everyday production, the amount of magnesium that we use is always the same. And most of the important aspects that we take with thermal analysis can be achieved with only these two types of cups. But that's correct. We have a third type with sulfur, especially for the study of nodularity.
Mm-hmm, mm-hmm. Thank you. Joe, there's one question from Samet Şahiner, one of the participants. He's asking,
Please.
He thanks for the presentation.
Thank
I
you.
want to ask about, is there any practical method for mass production applying? When we say mass production, it is serial production. From the thermal analysis point of view, is there any method or equipment which helps to use thermal properties in mass production?
No.
No.
Unfortunately, no. This is still a manual process, so we always need to manually take the sample from either the treatment ladle or the melting furnace and transport it to the cup. There is no automatic system to do this, so unfortunately this is still a really manual work to do for analysis. So
Okay.
The colleague asked, and I understand that he's probably working with something like a diesel line or something like that, and I work with a similar system. And unfortunately, every time that you do a magnesium treatment or every time that you do inoculation treatment, you need to repeat this manually. So normally you need someone to do this part of the work during production. There is no way to do this automatically, unfortunately.
Okay, thank you for the clear
Thank you.
answer. So another question is coming from Mehmet Saadettin Turhan. He's asking, from your presentation, we know importance of the GRF2 value for micro shrinkage. Which methods we do not use to bring this value to the desired range?
I'm not understanding the question, sorry.
There's a value, GRF2. That's a value which we are measuring time to time on screen, on thermal analysis equipment. That is related with the gray iron, GRF, graphical factor 2, graphite factor.
Okay.
Yeah. So the question is, from the adaptive thermal analysis system, that is a system we use in Turkey on different equipment. He says that the importance of graphite factor 2 is okay, but for microstructure, which methods we do not use to bring this value to desired range? So you did not mention from any range.
No, I didn't mention range. This is something that we don't achieve with the system that we have, the thermal analysis system that we have.
Okay.
But normally, to improve the production of gray cast iron, so to improve the graphitizing factor, we need to promote the formation of type A graphite. And one of the best inoculants to promote this is the strontium ones. So strontium is really good to promote type A graphite. So by using strontium, we can improve the gravitation. Sorry.
So there's an extra explanation.
It's the same as a VPS. Okay.
Yes,
thank you.
VPS.
Thank you. So it's easier like this. So the VPS. I will. Thank you for the note. I was not aware that. I will just go to one example. So the VPS, as we discussed, is the angle that is formed at the end of the solidification. So it is the angle of the first derivative, and the first derivative is related with the AOS value, with this temperature, the AOS value. So normally with VPS, this value means that when it is wide open, it means that a lot of graphite transformation happened at later stages of inoculation, later stages of solidification. So when we are going to decrease the temperature and we achieve the eutectic point, we have a transformation of graphite, of carbon in graphite, and the temperature continues to drop. And at the end of solidification, we still have a lot of carbides in the melt to transform in graphite. And this is not good. And the main reason why this is not good is that at this point, we already have a lot of austenitic structure formed in the cast. So even if you have a lot of expansion, it's not enough to compensate the amount of austenite that we already have formed. And the graphite should always happen more at the eutectic point to counteract the contraction of the austenite. So the way that we have to improve VPS is by having a better inoculation. So it's to promote an early formation of graphite. So if you have problems with the VPS, normally you have problems with porosity and micro shrinkage or even shrinkage, because you don't have carbon being formed at the stages where the carbon should form graphite. So the only way that we have to counteract this is to improve the inoculation process. For the particular case of gray cast iron, the best type of inoculants that we can use are the strontium ones, because strontium is with the gray cast iron. Basically, what it does is break the worm-like structure of gray cast iron and gives a smaller worm-like structure for the gray cast iron. So we have a smaller grain size. By having a smaller grain size, we have more points of nucleation. So we can have a smaller expansion of the graphite, and we can counteract some problems during solidification. So to improve the VPS with gray cast iron, I will probably try either an inoculant with strontium or try an inoculant with lanthanum, for example, because lanthanum can increase a lot the nucleation spots for the gray cast iron, and we can have more expansion and uniformly distributed in the cast. So using one of these, we can probably reduce a little bit the VPS and reduce the problems that we could have during this stage. So again, the problems, porosity and micro shrinkage, and if the VPS is really, really high, we can have some micro shrinkage as well.
Okay. Thank
you for the note with the VPS.
Yeah. That helps. Different companies are using different terminology. Yeah. So graphite factor 1 and 2 is used for this. So maybe the last question we are getting, because we have already exceeded the time.
Yeah. Sorry.
Yeah. Is there any different methods for taking sample after semi-inoculated metal? We couldn't solve this problem. We add inoculant inside of the quick cup, but result some 4 different type of inoculants there. It says that is. Are you able to read the question? Yeah.
No, unfortunately, there is not a lot of developments in the way that we take the sample. When I was working with diesel lines, so probably closer to the example that we are describing, we had really long spoons to catch the liquid metal before it entered the mold. So we catch the liquid metal after nodularization process and after the inoculation process, and we catch a small sample. But we really needed a long spoon to take it. So and we had space for that. I don't know if it is the case in this example, but if this is not possible, what I can say is that you could try to take the sample from the treatment ladle, and you can try to add the amount of inoculant corresponding to the volume of the cup. So, and I cannot give you values here because I don't know the volume that we are dealing with and the amount of inoculation that we are dealing with. But every time that I had some similar problem, I try to calculate the volume of the cup. And we know, for example, that we are adding 4 grams per second for 20 kilograms. And I do a quick calculus to know that for the volume, it is an equivalent amount of inoculant. I add it manually to the cup, and I pour it after treatment on top of the inoculant. And it is not 100% accurate, but it's the most accurate that we can have with this problem. But probably try to have a larger spoon, not too large because it could be difficult to operate, but try to have a larger spoon and try to catch the metal before it entered the mold, after the metal stream inoculation and after the magnesium treatment.
Okay, thank you. That is a hard topic.
Yes.
Hard to how to get sample after stream inoculation or
Yeah,
in mold
it's
inoculation. That is
it's not. It's
always
in mold. It's impossible. There is no
impossible. It's not possible.
everything that we do in mold, either inoculation or nodularization treatment, we cannot study it with thermal analysis because it's completely isolated and we cannot catch a sample.
That's
So we
true.
can only study everything that we do before the metal enters the mold.
That's true. That's true. So thank you once more, and
Thank you very much.
we we will get contact with Foseco Turkey to invite
Please,
you once more next year for a
of
seminar
course,
to
of course.
discuss this topic in detail.
My pleasure.
Yeah, that is okay. Thank you very much. Bye bye.
Sorry, I think there is
Is there
another question if you want me to
another
answer.
question? Another question. Yeah, from Mehmet Saadettin Turhan. Is there a method to stabilize the cooling time of the cup? Is it important to wrap it around?
Yes, the only thing that I can say regarding this is to always have the same amount of metal in the cup. So every time you are doing thermal analysis studies or you are doing thermal analysis during production, always using the same cup, because the amount of metal that you put in the cup can interfere with the calculations that the system does. So all the calculus that the system does related to carbon content, silicon, carbon equivalent, it is based on the amount of liquid metal that we use inside the cup. So the way to stabilize the cooling curve is to always use the same cup, always use
Same conditions.
the same conditions, so the same amount.
Mhm.
You can see this is a good example of this. Always use the correct filling, so every time to the top of the cup, and always do it like this, not sometimes less or sometimes more. Always try to use the same amount, the completely filled cup, and always the same cup. It's the most important part. Never compare two different cups, even if the volume seems the same. The position of the thermocouple could be different, could be in the center or could be in the bottom, and this could interfere with the readings, and you have different values for the temperatures and for the calculation of carbon and silicon. So always use the same cups and always use the same volume of liquid metal.
Okay. Thank you. Thank you, Joe.
Thank you.
Eğer değerli katılımcılar, öngördüğümüz sürenin aştık. Daha fazla sorusu olanlar Foseco Türkiye'deki ilgili arkadaşların burada iletişim bilgilerini paylaştıkları Alper Seçkin Bey ile temasa geçip ona soruları iletmeleri, sorulara yanıt almaları için uygun bir ortam sağlayacaktır. Biz bu webinarı kaydettik. Bu webinar paylaşıma açılacak ve benim teklif ettiğim gibi bu konunun bir seminer ortamında daha detaylı paylaşılması için çalışma yürüteceğiz. Eminim daha güzel, daha seçkin paylaşım ortamları yaratırız. Katıldığınız için çok teşekkür ederim. Güzel, sağlıklı günlerde görüşmek üzere. Hoşça kalın. Thank you, Joe. Bye bye then.
Thank you so much. Thank you very much for this opportunity.
Thank you. Bye bye.
Thank you.